Okay, so what I was hoping that we would talk about today are two of the important theorems that are derived from Hamiltonian mechanics that have to deal with phase space. One is the Liouville theorem, and the other is the Virial theorem. And so I'm going to suggest that we derive these and talk about what they mean a little bit, how they're used, and then if we have a little bit of time, we'll talk about Poisson brackets. So stop me, or if you have questions. I don't have a chat box up, so go ahead and just stop me if you have a question, or just speak up. Okay.
Louisville.
Hmm?
The second word, Louisville and
Virial, Virial.
thank you.
Okay, so to remind ourselves, phase space for one particle that can move in one dimension, one spatial dimension, we use the word phase space to mean the space that consists of the momentum of that particle and the coordinate position of that particle. So this QP space is a one-dimensional phase space, or is the phase space for one particle that can move in one dimension, one spatial dimension. So, for instance, if we have a object attached to a spring, so the force is minus kx, then what we mean is that there's some x-axis here, and this object is going to oscillate back and forth along the x-axis. So the x-axis is the q-axis, and in terms of the phase space portrait of this object, it would oscillate around in closed orbits, because oscillators, what this type of force just oscillate around closed orbits. Okay, good. Oh, hi, Daniel.
Hello.
So, so phase space for one particle moving in one spatial dimension is just a pair of P and Q. On the other hand, if we had one particle that could move in three spatial dimensions, the phase space that we would be interested in would be the space of Q vector and P vector, which you would ordinarily organize as x, the x momentum, y, the y momentum, and z and the z momentum. So the phase space of one particle moving in three spatial dimensions is a six-dimensional space. And so generally speaking, to describe the physics of a single particle that can move in x, y, and z, we're talking about paths through six-dimensional phase space. Now, while we're at this, I'm just going to sort of make an aside. We're thinking of phase space as the space of the Q and P. And the name that we want to apply to the space of Q and Q dot is called configuration space. Phase space is the space where the Hamiltonian function lives, and configuration space is the space where the Lagrangian lives, right? So the Lagrangian is a function of the position and the velocity, whereas the phase space is a function of the position and the momentum. And they're geometrically distinct spaces, and that actually becomes important in some of what we're going to talk about and some of what we're going to do. So phase space, for certain theoretical reasons, which we're going to start to see in a minute, is actually the right space to think as a physicist as the space through which particles are moving, as opposed to configuration space. Mathematicians frequently don't make a distinction between these. So if you pick up a book, like a differential equation geometry book, a book on geometry and differential equations, they'll take these two and basically say that you just assume the mass is 1. And then when you assume the mass is 1, then the q dot is equal to the p. And so there's not really a distinction between these two spaces, but geometrically and physically, they're separate spaces. Okay, so that's an aside that I wanted to make. So we're really thinking about today phase space and Hamiltonian dynamics. Now, so when we had one particle, we had 6-dimensional phase space per particle. So if we have a collection of n particles that can move in 3 spatial dimensions, that's going to be a 6-n-dimensional phase space. And we might organize that space as q vector I. I'm going to write it as q vector alpha, p vector alpha, where the alpha refers to the particles, right? So particle 1 would be q vector 1, p vector 1. Particle 2 would be q vector 2, p vector 2. So this space here would look like x1, p1x, y1, p1y, dot, 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 all the way to some y, s, p, y, s, z, s, p, z, s, where the particles are labeled 1 through s. Everybody good? Now, it's kind of traditional to take all of this and simply think of it as the collection QI, PI. So this is the phase space for my n-dimensional system. So, our n-dimensional system might be something like, on the simple end, it might be a pool table, right? And we might have some balls that have numbers painted on them, and they might be going this way and that, right? And so these balls would have positions and momentums associated with them, and then the dynamical interactions between those balls or whatever they are, right? The type of system, the system might be, we might be in space, and we might have some in dust grains that are interacting by gravity. Or we might have the air in the room, and each air molecule would have an X, Y, and Z position, an X, Y, and Z momentum. So however many 10 to the 23rd air molecules there would be, this would be a 6 times that number dimensional phase space. And the way we'll do things is we'll label an axis, we'll still draw phase space as QI, PI. So we'll still think of this in this way, but this QI axis now corresponds to, this is a real cartoon, right? Because this QI axis corresponds to 3 times the number of particles that I have available. And the PI axis is 3 times the number of momentum that I have available. But I can still think about a point here. And this particular point is at this time, one point explaining the configuration of all the air molecules. Right, so if this is my system, I have a given point would mean right now all the air molecules are in this set of locations moving with this set of momentum. Everybody good? And then they would be interacting somehow, and the flow is the dynamical motion through this space. So at some later time, the system may have evolved to be down there. Being down there means that the momentum are different and the positions are different, but however they're moving, the Hamiltonian dynamical system is moving under this flow.
So the point represents a set?
Yeah, so the point represents the entire configuration.
Yeah.
Right, so it represents the positions of all of the particles and the momentum of all of the particles. And then Hamiltonian dynamics just moves me forward in time. And the motion forward from the current set of parameters to a future set of parameters is the flow.
It's a simplification of like the whole system moving just down to one point. Is that?
Yeah,
good?
so
Okay,
when
that
we
makes
had
sense.
just the oscillator, we had Q and P where there was only one coordinate position and there was only one coordinate momentum. And so the flow was running around the circle, and any point on the circle was where that one oscillator was at that one time. And now what we're simply saying is, if I've got a whole bunch of particles, I have a point in phase space is the current state of all of those particles, their momentum and positions. And then the Hamiltonian dynamics will represent a flow, and the system is unlikely to remain there for all time. It's likely to move to some new position. But that new position is dynamically determined by the Hamiltonian of the system.
Understood.
Good? Okay. Now, what we're going to do is
I'm feeling some spider senses. I feel like there's something that's invariant here.
maybe at some point. Okay. So sometimes you see mathematicians refer to some region of phase space as D. That's the disk. And so some region of phase space D. And so now a region of phase space is not one configuration of the system. It's a whole set of configurations of the system. Right? So that probably pretty likely have fairly similar properties. Right? So from a statistical standpoint, all of the different points in this disk D are different ways to set up the system. They move the particle to a different place. Some of the particles have different momentum, right? So this disk D doesn't correspond to one instant in time of one system. It corresponds to a whole ensemble of possible systems. Okay. And now we're going to say that there is a density rho in D, and then the number of points in the disk D would be rho D volume. So we're going to say that N is rho D volume, and D volume is going to mean dq1, dp1, dq2, dp2, dq3, dp3, all the way down to dqs, dps, or written another way, right? It's dqi, dpi, and I guess if I really wanted to, I could write it something like that. So a capital pi, everybody knows a sigma of f sub I is the sum, right? So this idea of capital pi is the product. I'm going to leave the capital pi off, right? Okay.
Yep.
So we're going to think about this. And now the question that I'm going to ask is, under Hamiltonian dynamics, does this density change in time? An alternate version of this query, you can write it this way: under Hamiltonian dynamics, we're going to see that these are essentially the same questions, right? So the questions that we're asking ourselves that we want to ask is, if I start off with some disk here in the PI QI state, and so this disk corresponds to a bunch of different points, right? And each one of those points flows according to Hamiltonian dynamics somewhere, right? So after some period of time, this might be the disk at T1. This might be the disk at T2. There's nothing that says that the points will in the disk will maintain the outer boundary shape of the disk. But the question that I want to ask is the volume of disk 2 the same as the volume of disk 1? Or alternately, are the number of points in disk 2 equal to the number of points in disk 1? Or alternately, is the density of points in disk 2 equal to the density of points in disk 1? So the question that we're asking is, what types of things does Hamiltonian flow do to not one configuration, but a whole ensemble of configurations? Okay.
This is what I was thinking of. Yeah.
Yep.
So
Yeah.
I would almost want to say yes.
Well, we will examine whether or not Hamiltonian flow influences this. So here's how we're going to do that. I'm going to try to draw something a little bit more square. So let's suppose that my region now is kind of boxy, right? Then if Q dot I is a positive number, I would be, so if my Hamiltonian flow was such that Q dot I was positive, I would be coming in along that leftmost edge. So any Hamiltonian flow line that has Q dot I positive would be entering this region. Any Hamiltonian flow line that has P dot I positive is going to be entering into the bottom region. I'm going to say that this point down here is the point QI PI. And then I'm going to say that this distance here is DPI. So the distance, the height of my box is some small dp, and the width of my box is some small dq in all of my coordinates. And so the flow in on the left and the bottom edge is going to be leads to an increase in the density. And the amount of increase in density that I would have would be rho Q dot I dpi plus rho P dot I dqi at qi pi. All right, so if I had some little region and I'm running points in along this side here, that's this term here. It's dpi tall. So rho times dpi is essentially times q dot I is how many more points are coming in on the left edge. And the number of points that are coming in on the bottom edge is rho p dot I dqi. People okay with that?
Feel okay with that.
All right, so that's the points increasing the density. Now I'm going to redraw the same diagram. And trying to draw the same box. And I want to think about what's happening at the top edge and what's happening at the right edge. So now these flows are going to decrease the density. These would be flows out of the region for positive P dot I and positive Q dot I along the top edge and along the rightmost edge would be causing a decrease in the density. And this P dot I is happening at P plus dP, and this Q dot I is happening at Q plus dQ, right? So this distance here is dQi. This distance here is dPi. And if I started down here at the point QI, PI, then these flows are happening not at that point, but a little ways away. And the density rho might be different at a little bit distance away. Flow might be a little bit different at a little distance away. So the flow out is going to have the same form. It's going to be rho q dot I dpi plus rho p dot I dqi. But this whole thing here is happening at qi plus dqi. And this whole thing here is happening at pi plus dpi. So I'm going to take the flow out, which is happening a little bit over from where the flow came in. And I'm going to Taylor series expand the outflow so that I write the outflow as the flow at QIPI plus some derivative times some distance away. So this leads so I should do a Taylor series expansion here. Okay, and if I do that, the flow out, which was that, becomes equal to rho times q dot I evaluated at qi plus the derivative with respect to, I'm going to use a J letter now, rho q dot J d q I, and all of that is multiplied by dpi, and then I've got rho p dot I evaluated at pi plus the derivative with respect to pj of rho p dot j d p I d q I. Okay, so this Taylor series expansion took the first quantity here in red and said, okay, it's the value at the initial spot plus a derivative moving over a little bit to the right. Same thing on the other term. Great. Everybody good?
Following?
So now, what I wanted to get at, though, was how the density is changing in time in this region of space. So the way that rho is changing in time in the volume, dqi dpi, would be equal to the flow in minus the flow out. Now I've got a couple of different pages here, right? But my flow in, here was my flow in. And the flow in just has the q dot I dpi and the rho times p dot I dqi at qi pi. And the flow out has those two terms. They're the first terms. So when I subtract these two things, that first term dies and what's left are these derivative terms. Okay, so when I do the subtraction, what I get is d rho dt dqi dpi works out to be minus d by dq j rho q dot j plus d by dp j of rho p dot j, all multiplying dqi dpi. Okay, so if you subtract the two things that we had in our notes, that's what we get. we're now going to do several steps. We're going to cancel the dqi, dpi on both sides. All right, so we see that we have that on both sides. We're going to note that things like d by dqj of rho q dot j has an implicit sum in it. I'm going to put the sum back in. So I'm going to come back over here and say that I had to take this was really shorthand for taking a summation. So I'm going to put the sum back in. I've got here derivatives of products. So I'm going to use the product rule. Okay. And I'm going to take these two expressions. I got something on the left-hand side of the equal sign and something on the right-hand side of the equal sign. I'm going to move them together. Okay. So I'm going to do those 4 steps now. So I'm canceling the dqi, dpi, which was common to everything. I'm going to put explicitly the summation sign back in. I'm going to product rule out the products, the derivatives of the products, and move everything to the same side. When I do that, what I get is, well, I should probably start way over here. D rho dt plus the sum over j. Okay. D rho dq j q dot j plus rho dq dot j dqj plus d rho dpj p dot j plus rho d p dot j d p j equals 0. Okay, so now I got this expression. When I moved it to the same side, then that's where the equals 0 comes from, right? I used the product rule to take the derivative of 2 different products, and I put the summation back in. Okay, folks, good?
Yep, good here.
Okay, now, we've not yet said how we intend to enforce that the flow is Hamiltonian in nature. Here's how we're going to do it. Hamilton's equations of motion are q dot j is dh dpj, and p dot j is minus dh dqj. So that's Hamilton's equations of motion. And so I'm going to take this term dq dot j dqj. So this is the derivative of the velocity of the qj coordinate with respect to the qj coordinate. And I'm going to say that that's equal to d by dqj of dh dpj. Because that's Hamilton's equation of motion. So I'm going to stick Hamilton's equation of motion in for the q dot j. I can do the same thing for the p dot, the derivative of p dot j with respect to pj is d by dpj of minus dh dqj. Okay, everybody good with that? And I'm going to remind you that the order in which you take second derivatives, second mixed partial derivatives does not matter, right? You take dx, dy, or dy, dx, that doesn't matter. These are two different derivatives of the Hamiltonian, one with respect to the q's, one with respect to the p's, right? And they just have a minus sign between them, right? The only difference between these two terms is that minus sign. So if I scroll up a little bit, I have this term here and I have that term there. And those two terms add to 0. Because dq dot j dqj is the mixed derivative of the Hamiltonian, and dp dot j dpj is minus the mixed derivative of the Hamiltonian. And so those two terms add up to 0. Okay, everybody good? So now what we have found is that d rho dt plus the sum over j of d rho dq j q dot j. And let me actually, there was a q dot j here. I'm going to write it as dq j dt, right? That's q dot plus d rho dp j dp j dt. That's p dot is equal to 0. And now if I look at what's in the parentheses, if rho is a function of qj, pj, and time, and I wanted to take the time derivative, if I was going to take the time derivative of some function which depended on a whole bunch of q's, a whole bunch of p's, and the time coordinate itself, I would use the chain rule. I'd take the, well, I would have to take the derivative of all these coordinates and use the chain rule in doing so, right? And when I took the time derivative, I would pick up this first term. When I took the, if I wanted to, if this q depends on time, I'd have to take the derivative of rho with respect to q and then take dq dt. And then when I wanted to hit the time through the momentum, I'd have to take the derivative of rho with respect to the momentum and then multiply by the momentum dt. So what I'm trying to say is this whole expression here is nothing more than the total derivative of rho with respect to time. Which is a statement of the Liouville theorem. So what we found is that the density of states in the disk does not change in time as I undergo Hamiltonian flow. Right, so there's two, right? So the first thing to see is that I got this equation in the box, and then to recognize that if I'm thinking of the density as a function of the q's, the p's, and maybe t, what's in the box is just the total derivative with respect to time. That okay?
Sounds good. If the flow is therefore d rho dt is equal to 0, is there crazy idea? Is there a conserved quantity?
Well, yeah, the density of the space, the density of states in the space is a conserved quantity, right? So the interpretation of this, so the interpretation here that the Liouville theorem gives us is, so there's a couple ways to say the Liouville theorem. The density of states in a region of phase space does not change under Hamiltonian flow. Or I prefer to say it in the following way. You can see how this is going to be the case once you think about the density of states. The volume of a disk, say, with uniform density of space, so if you say that the initial density is uniform, then the volume of the disk in phase space is preserved under Hamiltonian flow. So if you have a Hamiltonian system, and this is your QI coordinate, and this is your PI coordinate, and this is your initial disk, right? Hamiltonian flow will take that disk and may distort it but it will have the same volume. It will not make the volume go to zero. So Hamiltonian flow preserves the volume in phase space of ensembles of systems. Now, that may, in isolation, that you might go, okay. But there's a whole bunch of systems that are therefore excluded from being Hamiltonian flow. So for instance, any system that has damping involved is fundamentally not Hamiltonian flow, right? If you have a damped oscillator, your phase space portrait can't, for instance, spiral down. So it's not possible to represent a damped oscillator through a Hamiltonian. So it becomes one of these really, and the reason for that is, let's suppose that you had a damped oscillator. If you started with some disk of phase space, so let's just say this is D0. At some later time, you would be at D1. And the volume of the taken up by those trajectories at some later time would have shrunk.
Yeah.
Okay, so Hamiltonian flow can distort a volume of phase space, but it won't change the amount of volume present. Now, you can do some really wacky distortions under Hamiltonian flow. There's all sorts of interesting things that you can do that are still Hamiltonian flow, but you won't decrease the volume under Hamiltonian flow.
When was the Liouville theorem conceived?
This was, it would have been the mid to late 1800s. So the Hamiltonian, these theorems in Hamiltonian dynamics were figured out in the late 1800s. Now, the importance of them didn't really become evident probably until sort of the rebirth of dynamical systems theory, say in the 1950s. So dynamical systems theory sort of becomes reborn in the 1950s, kind of by two to three groups. One group was by Schmale out at Caltech. There was an American group that was doing work, and the other group was the group by Kolmogorov, Arnold, and Moser, who developed something called KAM theory. And these were all Soviet mathematicians working in Moscow. So now, second thing. If you try to play the same game, it does not work out, because it is not true, that Lagrangian flow preserves the volume of an ensemble in configuration space. So there are subtle differences between how Lagrangian flow acts on configuration space and how Hamiltonian flow acts on phase space. And that reason, because of this, statistical mechanics works in phase space under Hamiltonian flow. So, the type of system that you would worry about, where you would consider an ensemble of possible initial configurations, is fundamentally a thermodynamical system. So why would I care about an ensemble of phase space conditions, right? So the air in the room right now, in my room right now, is one point in phase space. But if I considered a whole volume of phase space where I just let the particles move around a little bit, but maintain, say, the pressure, and maintain, say, the volume, and maintain the number of particles, and maintain the temperature of the gas in the room, I could carve out an entire region of phase space that corresponds to the same macro state of the air has filled the room with a certain amount of pressure and a certain amount of temperature and a certain amount of volume and number of particles, all your macroscopic state variables in thermodynamics, right? So the reason you would consider an ensemble, so an ensemble means a grouping of them, right? The reason you would consider an ensemble of phase space points would be to do statistical mechanics, to do the type of physics that you would want to do when you had more to work with than just one system at a time, right? If you wanted to talk about what's happening to an entire collection of systems, the way you talk about physics and thermodynamics, then you have to work in phase space, and then you have Hamiltonian flow. And so these theorems of Hamiltonian flow tell you something about the energetics that are possible when a system is left in thermal equilibrium by itself. Okay. You okay?
Very cool.
All right, so now, so that's the Virial theorem. Oh, no, I'm sorry, that was the Liouville theorem. Let's try to do the Virial theorem quickly. Okay, I'm going to do some things that you might go, why the hell would you do that? Okay, but I'm just going to do them. So I have some collection of objects, and R vector locates the position of each of those objects. So R vector alpha is the collection of vectors that locate all my objects. And I'm going to let them have momentum P alpha. So these are some collections of the positions and momentums. I'm going to define S to be the sum over alpha of, traditionally done as P vector dot R vector. So I'm just going to take the dot product of the momentum and the radius or the location and call that S. Okay. I'm now going to take the time derivative of S. So ds dt, there's a product here. I can pass it inside of the sum, is going to be P alpha dot R vector dot alpha plus P dot R. Okay, so it's a product, right? So I can just do a product rule. Okay, there we're good. Now, I'm going to take that quantity and I'm going to perform a time average. So these angle brackets mean take the time average. And what taking a time average means is you integrate the quantity with respect to time. And you integrate it, you do a finite integral from 0 to tau.
We did this in mechanics.
Maybe.
We did, I remember. Not the bracket notation for the time.
Oh, we did do a time, yeah. We did do a time average in one of our homework problems. Okay, now, the fundamental theorem of calculus says if you integrate the derivative, you just get the function evaluated at the endpoints. Okay, so not a big deal, right? So when I take the time average of the derivative of S with respect to time, I get S at the final point tau minus S at 0 divided by tau. Now, I'm going to give you two arguments, one of the either which needs to be true. Either I need to be the motion is periodic with tau being the period. If the motion that I'm interested in is periodic, where tau is the period, then S at tau would be equal to S at 0. And in that case, the time average of ds dt would be 0 because the motion's periodic and I'm using tau to be the period. And so I got S at later time minus S at starting time. And if it's periodic, then those are going to be equal to each other. Yep, everybody good? Okay. Or the system is bound. So we can't get far away. Now, if the system is bound and I can't get far away, then either this R here or this momentum here have to be modest in size, right? If the system is not bound and I can escape to infinity, then that R could become infinity. Or I might have a really big unbounded momentum. But if the system is bound, than like, a solar system or a galaxy or a cluster of galaxies or a cloud of gases that are gravitationally bound to each other or a set of springs, objects connected to springs. So I can't get far away. Then what I'm going to do is the following. I'm going to say that ds dt, well, I know that it is 1 over tau s at tau minus s at 0. I guess I can write it. Well, I know that that's true, right? And if that's the case and the system is bound, I'm just going to let tau get really big. So in the limit, if the system is bound, the time average would become, say, the limit as tau goes to infinity of s of tau minus s of 0 divided by tau. That's going to be 0 because s of tau and s of 0 aren't going to blow up, but tau is in the bottom and tau is going to go to infinity. And so I'm going to get 0 anyway. So now there could be systems that are not bound and there could be systems that are not periodic. But if my system is bound or my system is periodic, what I have found is that the time average of S is equal to 0. So, okay, great. Yay. Woohoo. So now I'm going to go back to my definition and pull out the two terms, right? My definition of ds dt had two terms. And there was a, they were added, so there's a minus sign here. Okay, so I have that. So the fact that ds dt time average was 0 means I can take the two terms and move one to the other side. All right. So now the key observation is that the kinetic energy is 1/2 mv squared, right? So that's 1/2 mv times v. So that's 1/2 p times v. So what I have over here on the left is actually twice the kinetic energy. On this side, what I have is the sum of the kinetic energies. And I got a factor of twice them, so I got a 1/2 on the side. And what I'm going to do with the p dot is replace that with Newton's law. So the sum of the forces is p dot, right? And this statement here is called the Virial theorem. And this term over here, the time average of the sum of F alpha dot R is called the Virial. So we've related the sum of the average kinetic energies, the average kinetic energy, basically the system, to something related to the force, okay? So now, if the force is minus the gradient of the potential energy, and the force is some k r to the n, then the potential energy is k r to the n plus 1. And my virial term how do I want to write this? Sum of force dot r sum of the gradient of u dot r. But if u has this form, then taking the gradient just brings down the n plus 1. Right? So if u depends on r and you take the and you're trying to take the gradient of it, then it brings down just an n plus 1. Oh, and I've killed the minus sign here because the force is minus the gradient of u. Okay. So this n plus 1 came from taking the derivative. It left me with just an n, but I'm multiplying by r from the formula, right? So this r here is in the formula again. So I'm going to pull out the n plus 1. And then I'm going to combine the first power of this r with the r to the n. So I got r to the n times r to the 1. So that gives me back the r to the n plus 1. And so now this in here is the total potential energy of the system. So the total kinetic energy of the system, time averaged, is related to the time average of the potential energy of the system. Making any sense at all? And now if U goes like K over R, that means that N was equal to -2, which is the gravity version. And so for gravity, what this says is that KE, the average total kinetic energy, is -1/2 the gravitational binding energy of the system. And so that becomes important in astronomy and astrophysics and in several applications. You can apply it to individual stars, you can apply it to clusters of galaxies, you can apply it to objects flying around in the galaxy, because you can measure the kinetic energy. You can literally look at a cluster of galaxies and measure the velocities that those galaxies are moving with by redshifts, by differential redshifts relative to the middle, right? So you can measure the kinetic energy of the galaxy, and therefore you can use that to infer a mass of the galaxy, because you would need a certain amount of mass in the galaxy to give you that, potential energy, right? So that what you do is you go out and you measure the kinetic energy, and then you can infer from the measured kinetic energy a virial mass, a mass of the cluster of galaxies, from using the virial theorem. But the line above it is true for any central force where the force is, K times R to the n plus 1.
Is this how like astrophysicists look at like for example a really known cluster is a Bell 2029?
Yeah. So, so people would have done a virial mass from that. So you can compare the mass that you get from this dynamics. Sometimes you see this called a dynamical mass, to a mass that you infer from X-ray modeling, to a mass that you infer from other things like gravitational lensing, right? So there's different ways to try to estimate the mass of a large object, and one is the virial mass. If you can measure the velocities of the objects in the big cluster.
So you could also use this to infer the mass of dark matter.
Because both the luminous and dark matter are needed. Okay, yeah. So what the mass are, both the luminous and the dark matter participate in forming the gravity of the cluster.
Mhm.
And so by measuring this virial mass, you're measuring the total mass of the cluster, including the dark matter. That's correct. Hey, so I see that it is 3:10. So that's a good time to stop.